Last time in 19.2 we talked about entropy, and we talked about the level of disorder, and we talked about S can be defined as the Q of the system over the absolute temperature. Today we're going to talk about, instead of measuring it in terms of energy or heat, we're going to talk about in terms of molecular motion down at the microscopic scale. If you remember, temperature is the average kinetic energy of the system. Back in the gas law chapter we talked about how there was a distribution of energy between gas molecules, where some of those molecules would have the most kinetic energy if Ke was over here, and at the bottom we'd have the progress, or the number of molecules at the bottom. So the number of molecules as they work, not all of them have the exact same. It's an average of everything. So how does this relate to entropy? Well, a guy named Boltzmann talked about microstates and how this results in terms of entropy or disorder. We're going to talk about something called a microstate. And a microstate is really defined as the number of possible positions, or a probability of all the little particles in a gas. Think about kinetic energy in a particular state. If you look at A, there's one molecule that is blue and one that is red. This is in your book as well, but the darker one we'll say is blue. So right now at the beginning of this reaction, the stopcock is closed, nothing happens. So we open up the stopcock and a spontaneous reaction occurs. It goes to more randomness. Once we do this at this microstate level, one possible arrangement is blue on the left and red on the right. Another possible arrangement can be the blue on the right and the red on the left. They could both be on, blue and red could both be on the left, or blue and red can both be on the right. Now, as we think about those would be called microstates. So since there are four possible arrangements of this, we would say there are four microstates, or four levels of disorder. Typically, the general rule of thumb is the more microstates you have, the more disorder that you could have. Well, this is convenient when you're working with only 4 molecules. But if we start looking at a mole of molecules, this gets really tough to track because we're talking about such a huge amount of those molecules. So what we do is we have to have some sort of equation or reaction to make this work together. So an equation that Boltzmann came up with is here at the bottom for point number 4. The entropy of a system is equal to the K, or the constant, times the natural log of W. Remember that W equals the number of microstates, or the possible arrangements where reactions can have. And in general, the higher number of the possible arrangements at the microstate level, that increases the disorder of the system. So in this example here, the 4 microstates, that would talk about disorder for us. Another thing that can lead to more disorder in a system, besides just microstates, is whenever we start thinking about molecular motion in general. When we talk about molecular motion, there's all sorts of motion that can happen. There are 3 basic types. Translational is the whole molecule moving from one place to the other. So I think about this molecule can move to the right, this molecule can move to the left, it can move down, it can move up. That would be a translational motion, where it can go wherever it wants to. Now, vibrational means that the molecule vibrates back and forth between 2 different spots. If you look at the picture down below, this molecule can vibrate in between these 2. Those are vibrational motions, or it can vibrate and rotate between all 3 of those different states. The more vibrations you have, the more likely you're going to have disorder. The final type of motion is rotational, where it can spin on its axis, like in this picture. When it rotates and moves around, that creates the disorder as well. So there are several different parts that can lead to greater disorder or greater entropy at this microstate level. Higher temperatures can lead to greater microstates and more disorder because you're going to have more kinetic energy. Higher volume, because you have more space for the particles to roam and vibrate and move. The more molecules you have, the more microstates you have, because they can vibrate and have translational motions, rotationals and translationals. And finally, Ke, the average kinetic energy of the system. All of those things increase the disorder or the entropy of that system. So the randomness or the energy of that system is really dependent upon the number of microstates and those variables. You can also think about it in terms of the dispersal or the randomness of the dispersal of energy. The more energy that gets dispersed throughout a substance or a sample, the more disorder you can have. So if we apply that to solids, liquids, and gases, we think about those three states of matter, and you think about the particle arrangements where the solids are going to have very low kinetic energy. They're going to be fairly ordered, where liquids are going to have more kinetic energy, not as much order. And then finally, gases are going to have the most space and the fewest particles. So these have the highest kinetic energy, and they have the most disorder. So when we think about the most disorder between solid, liquids, and gases, you would say that the biggest entropy, using big S to indicate the most entropy, would be there. And this would be the little s here for entropy, and then this would be in between. So the entropy would increase as the randomness of those molecules could work. Now, if I were to pack one of these with more of a particular type of molecule, and they could rotate, they could vibrate, and they could do translational motion, that could also increase the entropy. But in general, we can figure out the disorder based on the substance, whether it's a solid, liquid, or gas. Some general rules of thumb as well. If you go from something that's solid to aqueous, your S increases. Because you go from something that is a solid into something that's aqueous, you're dissolving in water, that's going to increase the disorder. If I go from something that has 2 gas molecules on the left of the reaction and I increase to 5 gas molecules on the right, S is increasing as well. So the more disordered, or the more microstates, or the more molecules you can get, the more disordered the reaction comes, the more entropy comes out there. And again, this is all kind of translated here with Boltzmann, when Boltzmann had S is equal to K times the natural log of those microstates. So the reason that's natural log is he looks at a collection of a log of those molecules, power of 10, the number of microstates you have, times his constant, that's going to tell you how much entropy. So now instead of just talking about entropy in terms of the energy of the system, we also have entropy in terms of the molecules themselves in the microstate level. We'll talk a little bit more about that tomorrow as I wrap this up.